This is Dr. John Bennett broadcasting from sunny Miami, Florida. We have today the pleasure of having Cyprian Ionita, PhD from the University of Buffalo. He's done some great work in 3D printing, mostly I know of the brain, and I believe that's what he's going to talk about today. And any questions that you have, you can ask questions at the Q&A. So welcome, Cyprian.
Thank you, John.
Yeah, thank you. Thanks for taking the time. And I just had a quick glance at your presentation. It looks like a really dynamite one. Anyways, just a few questions, Cyprian, before we start. You're originally from Albania. Did you go to university? Did you specialize in a certain area?
Sorry, I'm from Romania. Yes,
oh, I'm sorry, Romania. I'm sorry.
Yes, I finished my undergrad at University of Bucharest and applied nuclear physics.
Nuclear and physics?
Yes.
Okay, go ahead.
And then I came to Buffalo for medical physics, and here I took my PhD in medical imaging, mostly with applications to stroke and cerebral vasculature.
Well, that's interesting. There's a field, medical physics.
Yes, it mostly deals with, there's actually two parts of it. One, it deals with imaging, and the other one deals with therapy and cancer treatment. I am a medical physicist in imaging, so we're dealing mostly with X-ray detectors, CT reconstructions, MRI, and so far.
Well, I know radiologists, they have to take courses in physics. I guess you probably work alongside them, right? Radiologists?
Absolutely. I teach computed tomography for both biomedical engineers and for rad techs.
Okay. Okay, before you start your presentation on 3D printing, what else have you done in 3D printing besides the brain? Have you done anything else in 3D printing besides the brain? We
are working mostly on vasculature, and we are capable to reconstruct or create phantoms of entire vascular system, main vessels, mostly from femorals all the way to, let's say, middle cerebral arteries and beyond that. We are also doing coronaries as well as venous system. So we pretty much make like full body vascular models.
Okay, yeah, because I guess generally, I don't know if people know this, but vasculature can be anomalous, can be different in different people, right?
Absolutely, yes. Tortuosity, especially when we start looking at even at the aortic arches going between different types, type 2, type 3, bovine, and so far, that makes a lot of difference in navigating a catheter.
Well, prior to 3D printing, was it possible for surgeons to know the vasculature before they went in to the body, the brain, the chest, or whatever?
They were able to know the geometry before using various 3D imaging, cone beam CT, CT scans, or MRI, but they were not able to actually test an approach using catheter-based minimally invasive interventions. So now with the 3D printers, they have this opportunity, like when they have a unfavorable anatomy, to try to see if one approach is better than another. If a catheter can access the point where they want to reach. And we had it recently in media one example when the Dr. Siddiqui, my collaborator, was trying to treat an aneurysm in the MCA region, middle cerebral artery region, with a new device called Webb, and he wasn't able to deliver it. It was a phantom, and after realizing that, he changed the treatment and used a standard coiling technique.
Okay, so it is advantageous to have 3D printing nowadays.
Yes, especially, as I said, for patients with unfavorable anatomy, or when testing new devices that are not very common or on the market.
Yeah, and I'm sure we'll see its applications grow as time goes on, as we get better with 3D printers and the technology. Okay, Cyprian, could you start your presentation, please?
Yes. So today I just want to present a few slides on how to create these 3D models. Sorry about that. And
Okay.
I'll start with the 3D printer we are using. We are using a Stratasys 3D printer you see over here. It is it's a PolyJet kind of a printer, and we are using mostly a material which is called Tango Plus. And the general technique we're using to print this model is shown in here. We start with a normal angio CT scan. In this case, you see an angio as a brain. And we're using the normal software from Toshiba, the Vital Images, to create this, to segment these vessels. So just to show you other images, we can do brain vasculature, but at the same time, we can create also, as you see in here, 3D images of the coronary arteries, and this is no different from any kind of software on the PACS. This is actually what is coming from the CT scanner on the PACS system, and what Toshiba has implemented in Vital Systems has implemented direct STL output. What you see in here, it is we took the vessels and you right click on it and you say export as an STL. This is in general the file, and you can control the resolution of the stereolithographic file that goes through the 3D printer. So by selecting various resolutions. And once you're done with this, technically you obtain like a volume like this, which is you can 3D print it. It is not going to create a lumen, but you can create a model that you can hold in your hand and look at it. So this is the output directly from a medical unit, a PACS system, and I think this is relatively new. Mostly the engineers from Vital Systems, now owned by Toshiba, implemented this after they got quite a few requests from various vascular surgeons that they would like to have a file which they can 3D print. In the same way, even not only that, we can actually use rotational DSA. And out of all the images modalities, I would say rotational DSA, it is the easiest to actually 3D print, because the vessel is already segmented. You just take it, export it as a stereolithographic file, and then you correct this. Sometimes, as I show in here, this is an entire circle of Willis plus carotids. When you export it, sometimes this meshes come with errors depending on how much noise you have on the scanner. And what we do, we use a software which is referred as Mesh Mixer. That's available. It's free online. Anyone can download it, and it automatically will go through the file and will fix these errors. So you can see the back to the loop. We just take the CT scan, segmented. The PACS system outputs the STL file, and then we go through various kind of processing. We want to create inlets. If you want to connect it to a pump, for example, you need to make sure that these vessels are connected and they are closed. And here you see how we go through various through mesh manipulation to close all these vessels. Especially if you go deep in the brain where you have like small vessels past the middle cerebral artery, then you have to merge them and create only one outlet. So it is really, if you want to connect a model like this to a pump to simulate flow, physiological flow, it is really, really difficult to control that many outlets, for example, like in this part in here. So we merge them in one outlet, and we can we take the fluid out of the system pretty much. And next thing it is we adding a wall. We want to add a wall to create to maintain the lumen open. And as you can see in here, the vessel, it is significantly increased. But if you look on the sides, finally, on this semi-transparent kind of view, we have a lumen, and that all is done in Mesh Mixer. It's as I said, it's very very straightforward. We don't need to be a guru in 3D modeling or software work to create this kind of views. And finally, what we do, we add a support, as you see it in here, to hold the model to be just convenient for us. And that is again fairly easy to implement. And you see it in here, all the model. We have 2 carotids, 1 basilar artery, and only like 4 outlets where we merged all these vessels, including the ACA region, MCA left and right. So for 3D printing, as I said, we are using this printer, and we went for them because of this resolution, 16 micron layers when you print small vessels, and 20 to 85 in the X and Y direction as you print. I would say out of all the models that we are using, this is the most useful one. This is a Tango Plus. It is soft. It's a rubber-like material. And the neurosurgeons that use this model, they say it feels almost like like the real vessel. And these are kind of like what is inside this material. When we ask a chemist what exactly it is material, he said treat it as a polyurethane. So in terms of 3D printing, when a model comes out of the printer, is all embedded. You see here all this yellow thing. It is a support material, and the support material is both on the outside and inside the vessels. So what we do, we use a power washer, which and we clean all this material, blow it out. So now in this view here to the right, the model is clean inside the vessels. There is no residual materials; they are hollow. And you can see here, we can print something like this, and it will take about 9.5 hours for a full circle of Willis. Or we can print just the aneurysm. As you can see in this case, there is an MCA aneurysm, another small aneurysm in here. And that will take about 20 minutes to print at a full resolution, the highest resolution. Now, if I connect it to a pump and start injecting, this is the kind of images we are getting. So this is a contrast injection just on the right side of the carotid, and it looks pretty darn good compared to at least in the initial phase of the contrast injection. So this is another view where we inject fully into the entire system. Our models, this was an initial model, but as we advanced, our models became more and more intricate. So nowadays, they have far more vessels here on the distal part of it. So what we do for these models, and we have reported in AJNR and Journal of Neurointerventional Surgery, we place clots, and we take animal-based clots. We use thrombin, and we place them into a vessel, and we create a simulated stroke. And what we have done, we have tested three vendors, I think, on this particular for various devices and various methods to remove the clots. And we characterize these devices in terms of efficacy to remove this clots from the vessels. And we had 3 neurosurgeons, 3 different devices, tried various approaches, and we rated how these devices were able in retrieving such clots. And the approach was similar. Was a procedure. It was a neuro procedure. We inject the contrast. There should be some vessels somewhere in this area. They are not there. We create a roadmap. Then we go through the roadmap with a microcatheter. We pass the we pass the clot. We make a small injection to verify if the vessel is patent. Then we deploy the retriever, take off the clot, and then we reestablish flow in the area that was initially blocked. If people are concerned about what is the accuracy of these devices, of this procedure, here I have a comparison between what comes out of the printer and what we started with a CT scan. And on this vertical in here, it is the error between the two surfaces. And we are at about 150 microns, the average. We are quite at the level of the voxel size. A cone beam CT on an angio system comes about 200 microns resolution. So we are about the same order of magnitude in terms of errors on creating these models with what comes out of the CT scan. And the same thing you see in here, another aneurysm that we took, and the same, this even smaller errors that we see. So I think that's kind of like gives an overview of what is involved behind this this technology. I think the medical companies are working with us to give us the opportunity, the possibility to take these geometries and take them directly to a printer, as you've seen. And the part where you kind of have to create a vascular model, it is not very difficult. I mean, a person that has some experience with 3D model, 3D representations, or is passionate about working with a 3D software, will be able to master this process within about a week to 2 weeks.
Very good. Thank you for an excellent, clear presentation. Those are dynamite slides. And certainly this is a new area of medicine, which is very exciting. Now, just a few questions, Cyprian. I'm surprised you have simulate. You can simulate removal of a clot with the models. I'm surprised you do that.
Well, for the first application for us was actually to test devices in unfamiliar kind of in an unfavorable anatomy. That's a word that our neurosurgeons are using. Unfavorable anatomy.
Unfavorable anatomy.
So our goal was to actually test these devices and look into failure in really extreme cases. And the endovascular treatment planning, as we call it, just came as a application later. We had a few difficult cases, and Dr. Siddiqui, my collaborator, was thinking, well, can I try this approach and see if it works? And that's how we started the more profound application for treatment planning. But initially, we're just looking at these models to test devices and software for physiological measurements, like fractional flow reserve, for example.
Is it used yet to teach surgeons how to do procedures?
All our fellows are using them daily, I would say.
Okay.
Yes, there is residents and fellows. The models are continuously used.
Okay. And the doctor you work most closely with, Dr. Siddiqui?
Dr. Siddiqui is a research coordinator at UB Neurosurgery, University of Buffalo Neurosurgery. So.
Okay, he's a neurosurgeon or an interventional radiologist?
He's a neurosurgeon.
Neurosurgeon, okay. You probably work with neurointerventional radiologists too, right? Or not so much?
Not so much. Our collaborators are full neurosurgeons who do a lot of the vascular interventions. They are all trained and follow the legacy of Nick Hopkins, who started this whole center in here in Buffalo.
So the feedback from the doctors is pretty good, that they like.
Yes, they like how it feels. They said the friction and the haptics, as they call it, it's almost like in the patient. Not quite there yet. So there's still research to do. We're looking into methods to improve the friction, match the vascular coefficient of friction. We're also working into a rupture model. These models right now, they have the same tensile strength as a carotid, 7 megapascal, but they're not quite there. I mean, there's still work to do. They do not deform quite like a vessel, but that is more of a material that is laced, I would say, with Stratasys and their engineers.
Do you see this technology going to most major neurosurgical centers?
We are getting quite a few inquiries about how to make this phantom. Some other neurosurgeons are asking for models. We received a couple of requests for aneurysm, difficult aneurysm model from other universities. So and we made them and shipped them overnight for them to try.
Okay.
But this again were either pediatric or really difficult anatomy. Nothing ordinary, I would say.
Do other neurosurgeons send you like AutoCAD, like plans, and you print them out and FedEx them back?
They send me the DICOM.
Okay.
And once I have the DICOM, I can upload it in the vital images and automatically segment the vessel and 3D print it.
And you ship it to them.
Yes.
Okay. Wow. That's amazing. Maybe you guys will get busy doing a sideline of doing that.
And we didn't think it as a business. It still was an exploratory kind of a project. So we're just happy to do it at this point to test its capabilities and extend its application.
Yeah, and you mentioned it before. You mostly work with the brain and the carotids. Could you just touch briefly on what we were talking about before about the cardiac?
We can now we start looking into cardiac applications to extend the arteries for mostly in cardiac application for software testing. And what we are interested in is studying how accurate certain measurements done with software are as far as concerns tracking the contrast, for example. Look at the transarterial gradients, or looking at fractional flow reserve measurements with a catheter. So all these things are we are starting to look into it, and it will be very interesting to see if we can actually reproduce and create a model that is accurate from a cardiac point of flow through cardiac arteries.
Very good. Very exciting. Very dynamic field. Well, I'd like to thank you, Cyprian, for coming out today, and we welcome you to do as many hangouts as you want in areas in which you're working.
Problem.
And just hang out. We'll just end the broadcast and we'll chat.
No problem. Anytime. So our work is mostly presented at the SPIE Medical Imaging, and our students will be having quite a few presentations in the PAX session in 2016 in San Diego, where we kind of build a model, a cardiac model, which has a mitral valve, calcified mitral valve. So that is with dual materials, and it is just new. It's going to be reported at that conference.
Well, that sounds exciting. Okay, hang on. We'll end the broadcast. Goodbye.
Okay.